Now we're going to give some examples of adding numbers or numerical dates to geologic time, to rocks. The relevant pages for reading are shown there. And just to refresh your memory, there are things called relative ages, which is where we got the time scale. That is just saying that something is older than or younger than something else. So we use those terms that we talked about for the time scale. The Jurassic is older than the Tertiary, but it is younger than the Permian. Absolute is numerical. Anytime you see a number, it's numerical. And where we get that is from a study of radioactive decay. Now, we didn't even know about radioactivity, let alone how to measure it and what its implications were for rocks, until the 1900s. But remember, all those fundamental principles came in the 1800s, 1700s, and if you go as far back as Steno's, the 1600s. So this is the way we added numbers to all those accomplishments from before. So first of all, I need to talk about radioactive decay. I'm going to assume that most of you know what an atom is and that there are things called neutrons and protons and electrons. But just suffice it to say that there are different ways that these arrangements of particles can happen and can change. And so if you think about a nucleus, it has neutrons and protons in it, positively charged particles and neutral, or particles with no charge. Every once in a while, spontaneously, the nucleus will throw away what's called an alpha particle. What it literally means is that 2 protons and 2 neutrons fly away. They disappear. They leave the atom. We haven't forced it to happen. You haven't exerted a magnetic force. You haven't put a chemistry on it. You haven't heated it up. It just happens. It's spontaneous. When that happens, it will decrease the atomic number, which is the number of protons, by 2, and it decreases the atomic weight, which is the number of protons plus neutrons, by 4. There is a second type of radioactive decay, and that is beta decay. In beta decay, a neutron in the nucleus will just split. And if you think about it, if a neutron is 0, well, a proton is +1 and an electron is -1. Well, if you add a proton and an electron together, they cancel each other out and they become 0, or a neutron. Well, sometimes spontaneously a neutron will split into its component parts. The electron flies away, it's gone, and the proton stays behind. So what happens then is that the atomic number will go up by 1, but we really don't change the atomic weight at all, because the proton and neutron weigh essentially the same thing. That's because electrons weigh so little. There is a third type of radioactive decay that we call electron capture, and all this is, there is the reverse of beta decay. So in the diagram here, I've simply overlain arrows to show that instead of an electron flying away, it zings, it gets sucked in to the nucleus and it gets added to the proton to become a neutron. So then here, all of a sudden, it's going to reduce the atomic number by 1, but the atomic weight is going to stay the same. This never just happens sort of one. So an atom just doesn't decay and poof, it's over. There's usually a series. So it'll go through an alpha decay, then a beta decay, then maybe 3 electron captures, then another alpha decay. It just goes on and on like that. And as an example there, uranium-238, which is an unstable atom, will decay to lead-206 in 14 different steps. It does those 14 steps regardless. It never adds a step, never subtracts a step. It does them in the exact same order, and it does them at the exact same speed or time. Which brings us to how we measure this. We talk about the half-life of an unstable parent isotope or atom. And it's the time it takes for 1/2 of them to decay to stable daughters. So if you've got unstable uranium, a pound of it, how long is it going to take for 50% of it or half a pound of it to become that lead. This rate is a constant. I can't emphasize that enough. This rate never changes, doesn't speed up, doesn't slow down. And we have a bunch of these that we know of that work very well for geology. In geology, we want half-lives that are very, very long. And so look at these here. The half-life of uranium-238 to 206 lead is 4.5 BY, which is billion years. The half-life from uranium-235 to lead-207 is 704 million years. The half-life for potassium-40 to argon-40, 1.3 billion. Really big ones. So if you have a rock and a way to measure the amount of uranium in it and the amount of lead in it, you can tell, and you know how fast one decays into the other one, you can tell the age of the rock. Half-lives in geology. How do we do this? We do it with igneous rocks. I said igneous rocks aren't going to be so important for this class, but they are here. If you look at this rock here, granite, you see all the different crystals, the gray ones, the black ones, the white ones, these sort of orangish ones. And every one of those little crystals you can think of as a little box that contains some radioactive isotope in it. And as time goes by, it's slowly going to decay from one to the other. The boxes are tight, meaning if you look at a single individual, say, orange crystal here, a feldspar, it's just going to slowly turn all of its parent into daughter. No daughter leaks in, no daughter leaks out. No parent leaks in, no parent leaks out. It's a tight box. As it sits there, this happens. So, when does it start? It starts the moment a crystal becomes a solid. So lava belches out onto the surface of the earth. It's liquid, it's molten. When it cools and hardens, the second it becomes a crystal, it has 100% parent. And over time, that percentage parent is going to get smaller and smaller and smaller, and the percentage daughter is going to get bigger and bigger and bigger. Well, here's the problem. Think back to this. We are going to talk about fossils in sedimentary rocks, but these absolute age dates, these numbers, come from igneous rocks. So rocks that have fossils in them, we don't get these numbers for. There's one exception, and that's carbon-14, and I'm going to talk about that in the next lecture. But most of these, it doesn't work. So what's our resolution? How do we solve this? First of all, we age date. We take igneous rock samples anywhere we find them, but especially when they are in contact with sedimentary rocks. So the upper picture is a cartoon, the lower picture is a field photo. The black rock that's standing vertical is an igneous rock. It's a type of thing that we call a dike, and we can get an absolute number from that. The rocks next to it, around it, you can see the bedding layering in it, are sedimentary. This is a beautiful example of the cross-cutting relationship that Lyell told us about, that this rock here must be younger than the rocks it cuts through. So, if we can get a date for the rock that is cutting through, the igneous rock, and let's say for this example here, we know that it is 185 million years, we then know that everything that it cuts through has to be older than 185 million years. So if you have a fossil like this, here's a dinosaur bone in this rock, and it's cut this way, I can't tell you exactly how old this bone is, but I can say that it is older than this rock that cuts across it. And this is just one example. What if you have a situation where you have another igneous rock that cuts across all of these, or cuts across these, or you go through different places, and essentially you go around the globe looking for places where igneous rocks have cut across sedimentary rocks. We get the geologic calendar of relative dates, Cambrian, Ordovician, Silurian, Devonian, from the fossils and the sed rocks, and then we are able to pin numbers on them by these igneous rocks cutting through. This then takes us to the radioactive decay curve. This is a very important diagram. It will be on exam 1. And this, first, I want you to look at the axes of it, because this is going to be a useful thing, and it's what we use to age date rocks. The bottom axis, or the x-axis, has the number of half-lives, and these are simply counted. Notice in the extreme left, it starts at 0. It goes 1 half-life, 2 half-life, 3, 4, as you move to the right. At 0 half-lives, remember I said we have 100% parent. So this axis, the y-axis over here, is measuring the percentage of parent. So at time 0, remember that's when that crystal first forms, boom, we're right up here at 100% parent. As that crystal sits there, the parent decays, and we get less and less and less of it over time. When we reach 50% parent, so you look at the y-axis here, 50%, you go over and you go where it intersects this line, you go straight down, that is 1 half-life, 50% parent. Now, don't be mistaken and think, okay, 1 more half-life and the other 50% gone. So it's not 50%, then another 50%, it's 50%, half, and then half of that half. So half of 50 then is 25. Half of 25 is about 12 and a half. Half of 12 and a half is 6 and change, etc. And so you see this is called the exponential decay curve. The percentage of parent keeps dropping, 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 dropping. And notice you're always getting half of what's left. Eventually you'll peter out off the chart to the right to nothing. The little dashed line is the percentage of daughter. And notice at time 0, we have no daughter. And as defined, when half the parent is gone, half of the daughter is there. And that's where those two lines cross. And so this line gets bigger and bigger and bigger. And notice it's a mirror image of the line over here. This is the whole basis of radioactive decay. If we can measure the percentage of parent or the percentage of daughter, usually the percentage of parent, and we can use this chart, we shoot down, and if we know what the half-life is, we can calculate the age of the rock. And that's the next lecture note that I'm going to be talking about.